All right, everybody, welcome to week 13. This week we are going to be looking at polar coordinates. This corresponds with chapter 9 in our textbook here. And so we're going to start by defining our polar coordinates here. So in general, what you should be doing right now is you should be using this video as a companion with the notes that I wrote for the class. You should be reading the notes. You should be attempting the problems. You should then be watching the videos to verify your answers to the problems and get a little bit extra help, and then moving on with the document. So you should be working with the written, the notes document as well as this video sort of side by side here. These two things correspond. In the document that you have for your notes, there are lots of section titles that are underlined. I'm going to try and do my best to keep a blue underlined section title to match in the video what topic we're talking about from the notes here. So starting with defining polar coordinates here, what we want to recognize is that we've really spent our entire graphical lives dealing with what we refer to as rectangular coordinates, also known as Cartesian coordinates. Those are from René Descartes. That's where we get the word Cartesian from. That's the dude that invented them, smart guy. And the thing to realize that's a little bit strange about our Cartesian or rectangular coordinates is that everything needs to be defined in terms of sort of rectangles. We only move purely horizontally and purely vertically when we live in a rectangularly defined world. If I were to identify some point in space xy for you, then you know that the x coordinate means that you move exclusively to the right by x units, then move exclusively up by y units. But there are some shapes in this world, like circles, that matter a lot to us in this class that are actually really poorly defined when we think of things rectangularly. Instead, lots of shapes are better described if we instead describe how to get to the points on the shape in different ways. What we're going to talk about now are polar coordinates. And polar coordinates, rather than describing an instruction set to get to a point based on left, right, and up, down information, will instead give instructions that are based on an angle at which to travel and a distance at which to travel that angle. And that makes kind of a lot of sense as far as lots of instruction giving goes. If you're walking in a neighborhood trying to get to somewhere, you might give somebody the instruction set of walk 3 blocks east and 4 blocks north. That's rectangular instructions. You could give an XY coordinate associated with the location where that person's trying to travel to. Alternatively, if you're flying in an airplane, you should know that airplanes don't fly only east, west, north, south. Airplanes are going to do other things like, say, for example, fly at an angle of 30 degrees north of west for a distance of 500 miles. The distance that they're traveling is not an east-west or north-south distance. If we're traveling 30 degrees north of west, 30 degrees north of west would be right here, and we would travel 500 miles in that distance. I think both of those instruction sets make a whole bunch of sense for us to explain, and so hopefully it makes intuitive sense to you that it seems reasonable that we should have a different measurement system for identifying locations in space. Rather than listing our grid coordinates like in a neighborhood setting, we could talk about our polar coordinates, our angle and our distance at which we are traveling, rather than how much left, right, how much up, down do we want to travel. Finally, just before I erase this picture, you should notice here that I intended to draw both these points at the exact same location in space. This suggests to us that for any point that we know the XY coordinates for, maybe we're interested in finding out the associated R theta coordinates for, and vice versa. Now, actual thing before I erase this, I'd just like to say, just as we always write our ordered pairs as x comma y, and we never write y comma x, here we very typically always write these as r comma theta and never theta comma r. That's not for any real reason, that's just for consistency's sake. So if I say to you, here's a polar coordinate, you'll know that the first term is always going to be the radius, the second term is always going to be the angle that's associated with where that point is in space. So let's go ahead and plot a few points here. I just want to point out that there's some slight oddities that are associated with polar coordinates, something that's a little bit different than what we're traditionally used to in our rectangular coordinates here, but I don't think it's anything too crazy. So let's go ahead and look at example 1. So in example 1, I'm just asking you to plot 4 different points. So I'm just going to make one big graph and identify P1 through P4 all on that one graph. So we still have an x and a y axis. This is still helpful for me to think about where we're located in space. I'm just not going to define any of my terms in terms of that here. So we've been given, sorry, I'm going to actually move this over slightly here so I can write my P1 through P4 right here. We are looking at P1 being 2 pi thirds. P2 is going to be 1/3. P3 is going to be -2, 90. And P4 is going to be 0, 3 pi halves. So here is my, still looking at what I think of as an XY plane. I'd like to identify these 4 points locations in the plane. So we want to remember that we're always thinking of all of these points in general as r comma theta, radius and angle. When we say angle, we mean relative to this being 0 degrees, how many degrees should we open up, right? So our angles are always relative to the positive x-axis. Our radius is the distance that we are traveling along that angle. So our first one is, I think, the only one that's very comfortable for us to do right here, 2 pi thirds. This says to me, on the line that makes an angle of pi thirds with the positive x-axis, travel a distance of 2 units. So I know that pi thirds is going to be our angle out here. And I'm thinking to myself, I would like to travel 2 units along this line. Now, I'm not putting any numbers on my graph right now. I guess what I'm going to try and do is at least make them relative to each other. I'm going to make them appropriate distances out here. But this should be a distance of 2 units in the angle of pi thirds right there. Remember that pi thirds is really 60 degrees. And so maybe I'll get rid of my dashed line there associated with pi thirds. And we can just call this point in space here then P1. We've gone an angle of pi thirds, and we've gone 2 units in that direction. I don't have any numbers on my graph, so it's hard for us to see the actual 2-ness of it right now, but we'll at least make these relative to each other, the appropriate sizes. For P2, the reason I'm giving us P2 as an example is because this is a little bit awkward for us to think about. If I said to you, plot the ordered pair 1, 3, I would absolutely expect you to be thinking XY coordinates here. I think when I see things like 2 pi thirds, that screams polar to me because I know that polar form is going to have an angle in the second slot right there. This doesn't look like an angle to me. But if I'm telling you this is a polar coordinate, then that means to me my radius is 1 and that my angle is 3. So the way that I'm going to think about this one right here, oh, by the way, I did put a degree symbol on the 90 and I did not put a degree symbol on the 3 in the notes right there. So I'm going to go ahead and interpret this 3 as a radian amount, and here's what I'm thinking. How do I graph 3 radians? Where is that located? Well, what I know is that pi radians is sitting over here at 180. Here's pi radians. And pi is like 3.14. 3 should just be very slightly less than that, right? So I'm picturing to myself that 3 radians should be like on that line right there, since 3.14 radians is all the way to the axis, and we would like to travel only 1 unit along that line right there. So if this distance was 2 units, then we should be only going half that distance here to get to our point right here. I think that that right there is a good representation of our point that is associated with 1, 3 in polar coordinates right there. So I'll go ahead and identify that as P2. Our third one here is a little bit awkward. Here this says I want a radius of -2 and I want an angle of 90 degrees. What in the world does it mean to have a radius of -2? I almost kind of, in a sense, I like that this is an option for us, but I kind of dislike the, well, I don't know, a little bit of the confusion that it creates right here. Generally, we should think of radii only as positive values, and in general, if you were to ever compute a radius, you should always be getting out a positive value. Or a hypotenuse of a triangle, we should be always getting positive numbers because that represents a distance. But in this case, how should we interpret this? Well, what I'm thinking to myself is the angle of 90 degrees is up here. And what I'm saying to myself is I would like to travel -2 units in that direction. Well, -2 units in the up direction is the same thing to me as +2 units in the down direction here. So I'm kind of thinking to myself that I should really be traveling 2 units, which is the distance from the origin to P1, in the direction to get to P3 down here. So P3, since 90 degrees is up, We wanted to go -2 units in the 90-degree direction, so we just went in the exact opposite direction of 90 right there. So there's my P3 location. A little bit weird, but technically that's the appropriate interpretation for this guy here. This will be important for some of our weirder graphs that we're going to see. And finally, our point P4, this says, in the angle 3 pi halves, the down angle, go a distance of 0. Well, this P4 point's actually going to be really easy for me to graph right here because I'm only going 0 units away. So the reason that I'm giving you P4 here as part of an example is to say, I don't care what the angle is here. If you go no units, then you're sitting at the origin. I could have literally had any angle sitting in this slot right here, and I still would have graphed P4 at the same place. It said our distance from the origin was 0. So any ordered pair in polar with 0 in the first slot will always end up at the origin right there. You can kind of think to yourself that maybe you're like a person standing in a grid, and maybe you're like looking a different direction, but your position is the exact same. I might be looking south as I stand in that position, but my position is still the center of our coordinate system that's out there. So graphing these things in polar, this is pretty much our typical example is things like P1, pretty simple out there. You should realize that you might want to be able to interpret 3 as like some number of pi out there. 3 is a little bit less than pi, so I know where this angle is represented. Negative radii just mean travel in the opposite direction of your intended direction there. And a radius of 0 just really means that we're sitting at the center right there. So that's all we should have seen for our example 1. So coming up here now, what we're really interested in doing is maybe identifying what is the equivalent rectangular coordinates that corresponds to each of these polar coordinates. So a very important thing that we want to do here is discuss what are our conversion equations. If I give you a point in polar space, how can you determine for me the equivalent location in XY rectangular space here? So let's go ahead and take a look at our conversions and then do several examples with those. So hopefully you have recognized the very, very repetitive shape that's cropping up in this picture here. If I'm given XY coordinates, that says go to some X value, then go to its corresponding Y value and plot that point. Alternative, so this is giving me an X distance and it's giving me a Y distance. Alternatively, if I wanted to think about this exact same point in polar space, that would say to me, go some distance directly from the origin to that point and do that at some certain angle. So our triangle that we are interested in here is this guy. We have an X amount, we have a Y amount, we have a distance from the origin, and we have the angle that the ray from our point through the origin is making with the positive x-axis. That one always gets really wordy for theta. The angle theta is the angle that the ray from our point through the origin, the angle that that ray makes with the positive x-axis. So all I want to do is use this triangle here to help me identify our important equations that we've got listed. So this is really important. If you haven't done this yet, you should really pause this video right now and do this. This is like the most important thing of this unit. Our goal here is to say, if I was given rectangular coordinates of x and y, could you determine r and theta? So algebraically speaking, this says to me, determine an equation for r that depends only on x and y. Determine an equation for theta that depends only on x and y. Then we'll flip this question around. Then we ask, if we were instead given polar information of r and theta, could we solve for what x and y must be? Algebraically, this says to me, write an equation for x using only r and theta. Write an equation for y using only r and theta. You should come up with those 4 equations right now and then pick back up with this video. Do it. Okay, there we go. So you've done it. So let's kind of walk through what each of these is going to look like right now. So I'm just going to do these in the order. I have like a bulleted list there, or a 1, 2, 3, 4 in the notes. I'm just going to fall through the order of that 1, 2, 3, 4. So first things first is I'm going to determine a formula for r in terms of xy. So if I want to relate r, x, and y, I'm asking you, do you know any relationship between those three values? And very hopefully your answer is yes. We know that in any right triangle, the Pythagorean theorem applies. So I want an equation for r, but what I know is r squared equals x squared plus y squared. What I want is an equation that just gives me r. So let's just go ahead and take a square root on both sides here. You should remember that generally, algebraically, this should introduce a plus or minus for us. But as we said, we're really only ever going to give positive r's as answers here. If somebody gives us a negative r, we can interpret a negative radius, but we should avoid intentionally having negative radii on our own. So we've got our first of our four conversion equations right here. Our radius is going to be equal to square root of x squared plus y squared. I'll make my list over here. I'll do my work over here. So now we found our equation for r. I think that's our easiest one. Potentially our hardest one, maybe, although none of these are very, very difficult here, is we'd like to determine an equation for theta in terms of x and y. So when we're doing this equation here, I'm thinking to myself, I know x and I know y. I'm thinking to myself, I don't know r. That's polar information. I only know my rectangular information here. So I want to make a statement about theta. So relative to the angle theta, what sides do x and y represent? Well, y is opposite, x is adjacent. That just screams tangent to me. So I'm going to make my general statement here. Tan theta equals tangent of theta is opposite over adjacent. That should be y over x. And again, what I'm interested in doing is not making a statement for tangent of theta. Just like before, I wasn't interested in making a statement for r squared. I want to know r equals. I want to know theta equals. So what am I going to do to get theta here? I'm going to go ahead and apply a tangent inverse on both sides. Y over x. So it looks like in any of our rectangular scenarios here, if we know x and y, we can just plug it into the tangent inverse function right here, and we'll have our value of theta. Similarly, if we know x and y, we can plug it into our, essentially this is like a distance formula equation right here, a Pythagorean theorem statement, and we can directly solve for r. So the good news is we've already built two of our four formulas here, and the next ones are not a whole lot more difficult than these two right here. I think they're pretty equivalent, so let's just keep on going. So what we've done so far is we have figured out how to convert from rectangular information into polar information. Now we'd like to flip this around. Now we'd like to say, if we knew the polar form, how could we get the rectangular form? So now let's go ahead and switch this. Before we were looking for things in terms of x and y. Now we want things in terms of r and theta. So let's find x in terms of r and theta, and then we'll do y. So now we're switching what we say that we know. What we're saying that we know now is we do know r and theta. What we don't know is x and y. I want to come up with first a statement for x. So I'm just going to kind of cover up my y information right here. If I wanted to describe how x is related to r and theta, well, I've got an angle that I need to work with here, and that angle says to me I should probably use a trig function. So what side lengths do x and r represent relative to theta? Well, relative to theta, r is the hypotenuse and x is adjacent. Adjacent and hypotenuse, that says to me some cosine stuff. So I think I can make a statement that looks like cosine of theta equals, and cosine of theta here is adjacent over hypotenuse, that's x over r. But what I'm not interested in here is making a statement for cosine of theta or a statement for x over r. I want just x equals so that I can solve for x given r and theta. Well, that's pretty easy to do right here. I can just multiply r over to the other side, and I'm going to get x equals r cos theta. So we've got another conversion equation here. Finally here, the only other statement I'm interested in making is the partner statement here that goes along with this. I'll say x equals r cos theta here. Finally, we just want to say, how do we get y in terms of r and theta? This statement's going to be very, very similar. So now x is out of the picture, so now we're trying to relate r, theta, and y. And here it looks like we can make a very similar statement. It looks like here, relative to the angle theta, y is opposite, r is hypotenuse. So that says to me sine of theta equals y over r. And again, we're interested in making a y equals statement, so let's multiply both sides by r, and we're going to see y equals, y equals r sine theta. So y equals r sine theta. So these four equations right here are all we'll need to do our conversions between our two systems. If we know x and y, we can get r and theta. If we know r and theta, we can get x and y. We can now go both directions here, converting from polar into rectangular or from rectangular into polar here with these two sets of equations right here. And finally, I did put this little note in my notes right here, which is to say people know that they're supposed to be able to do this a lot, like after trig class, when they're either in my algebra class or in my calculus class or something. And when people say to me, oh shoot, I don't remember what my trig conversion is to get theta out. And as I say in my notes, all I do is just frown at those people and give them the crazy eyes. And all I do is just draw this triangle and just walk away. This triangle is really all you need to remember. Memorizing formulas is crazy. Memorizing pictures makes sense. This picture contains all four of these formulas for us right there. I really do think you should be able to derive those formulas. All of those took like one algebra step each to come up with their statements there. So I do think the actual act of producing these formulas rather than just using them is really, really important. And they're all tied to this very simple picture, this picture that we've been using. Man, we have beat this right triangle to death this semester. And we're just doing more of that right now, just giving the typical labels and identifying how do we solve for any one of the pieces of information out there. So let's use these now to actually make some of our conversions happen. So let's go ahead and pick up with example 2. I am going to just move these over on my board here so that I kind of have these for the rest of this set of videos here. So r equals square root of x squared plus y squared. We've got theta equals tan inverse of y over x. We've got x equals r cos theta. And we've got y equals r sine theta. Let's get this in blue here. Keep our structure. And let's take a look at example 2. In example 2 here, we're looking to convert polar points into rectangular. In example 3, we'll convert rectangular points back into polar here. So we've been given the points 3 pi sixth, and so what we would like to do here is convert this into xy. So let me maybe write it like this. I'm going to write this as r theta equals 3 pi sixths. And what we would like to know is what is the corresponding xy location of this point. Graphically speaking, I'm going to go in the pi sixths direction, the 30-degree angle direction, and I'm going to go 3 units in that direction. So I'm sort of picturing there's my pi thirds angle right there, and we're going to go 3 units in that direction. I'm always going to draw these because I want to really make sure that I'm doing this right. I mean, I haven't done this yet, so we should always get some sort of visual confirmation of what we're doing here. So it looks like I know that r equals 3 and theta equals pi sixth. It looks like what I want to know is what's the value of x and what's the value of y. This should be pretty straightforward here. To solve for x, we're going to use r cos theta. Notice how easy this formula is to remember, by the way. Cosine is what's always been giving us our left-right amounts. That's our x amounts. Sine is what's always been describing our vertical amount on our unit circle. It's associated with our y values here, so hopefully that's pretty easy for us to remember. So here, our radius is 3, and we're going to take the cosine of pi sixths. So we just have to ask ourselves, what is the cosine of pi sixths? I see that pi sixths, the x amount is the bigger of the two, so I'm going to get a root 3 over 2. So here I'm going to get 3 root 3 over 2. This 3 is the radius 3. Root 3 over 2 is the cosine of pi sixths right there. Very, very similarly, we can do this for y. Nothing too exciting happening here. R is sine theta, so we're going to get y is going to be 3 times the sine of pi sixths. I can see that the height of this point is the smaller of the two, so that's going to be our 1/2. So we should be getting that y is 3 over 2. The 3 is the radius 3. Dividing by 2, that's our 1/2 that came from the sine of pi sixths right there. So there's our first example for part A. Now let's go ahead and do and oh, by the way, so I want to verify, right, that this actually worked out. What I do see here is that this number is root 3 times as big as this number. So I do have a positive x, I do have a positive y, and x is bigger than y. Positive x, positive y, and x is bigger than y. That's about as good as graphical verification as I think I'm going to get for some of these right here. But I have at least confirmed our points in the correct quadrant. I do seem to have the correct, like, is x bigger, is y bigger kind of thing going on right there. So as far as validating this answer goes, I feel pretty good about this compared to the graph that I drew associated with my original point. Let's do this again, and let's get ourselves our new r and theta point right here. I didn't need to erase that one right there. Still have our same things that we're about to do here in a second. So in our next example here, we're going to go ahead and look at negative 250 degrees. So a little bit weirder here. I'm given an angle in degrees. I'm given a negative radius here. So I'm picturing for myself, generally 150 degrees is this guy right here. It's sort of 30 degrees off of our 180. But we're going to go negative 2 units in that direction. So I'm actually going to end up over here somewhere. So I'm expecting a fourth quadrant point. I'm expecting a positive x, but a negative y when we go ahead and look at this guy here. When I compute this then, x is going to be negative 2 times the cosine of 150. When we look at the cosine of 150, I'm seeing that this is, we have a reference angle of 30 degrees out here. So cosine of 150 looks like it's the bigger of the two. So I see I'm going to get root 3 over 2. But it's cosine, so we should be getting a negative root 3 over 2 because it's to the left. And so it looks like we have negative 2 times negative root 3 over 2. And so I'm seeing here negative and negative are going to cancel, and times 2 and divided by 2 are going to cancel. And it looks like our x value here should just be exactly square root of 3. Similarly, over here, we've got y equals our radius of negative 2 times the sine of 150. When I'm picturing the sine of 150, I'm picturing the height associated with this angle on the unit circle. I'm seeing that the height associated with this angle is the smaller of the two legs, so I'm picturing a 1/2. And I am seeing that this height is positive, so I should be getting a positive 1/2. And so I'm seeing here, it looks like we're just going to get a y value of negative 1. Does this make sense to me? Well, what I'm seeing over here is the point that I thought we should be getting had a positive x, had a negative y, and it looks like x was bigger than y. And we see all that down here. Positive x, negative y, square root of 3 is bigger than 1. So I do have more x stuff than y stuff. So I do feel pretty good about this right here. Keep drawing your sketches. Always, always, always. This is not exactly effort that it takes to draw that picture, but it does help me verify all the things. If you were to have dropped any of the 3 negatives that cropped up in our formulas here, we would have been able to easily identify that by just having drawn that picture. So always draw yourself these little sketches that are helping you verify all of your answers here. So now that we've done example 2, converting into rectangular from polar, let's go ahead and flip that now and start with rectangular, and let's convert into polar. We're going to see that we do have one light little snag, not really a snag, but just a one. This was pretty straightforward. We literally just plugged numbers into a thing and got numbers out and we're good. We verified it with a picture, but we were right both times. We will see that there is a little bit of something we got to watch out for here. Oh, that was B, by the way. I didn't change my A to B right there. There's a little bit of something we want to watch out for when it comes to our conversions in the other direction here. So let's take a look at example 3. In example 3, we've been given 2 rectangular points, and we would like to convert them into polar. So our first point we're going to convert to polar is 3, 7. Always, first thing I'm going to do is just give myself the lightest little sketch of this thing. I'm not even putting numbers on it. I'm going to go 3 to the right and I'm going to go 7 up. So something like that right there. I'm picturing a first quadrant point. I know that my x value is smaller than my y value right there. And if I'm just estimating this right now, by the way, then I'm picturing that we're going to get something that is at an angle of like, I don't know, 60 or 70 degrees, something around maybe like pi thirds. And I'm expecting this to have some moderate length in there. If we're going to go 3 to the right and 7 up, then I'm kind of expecting that we're going to get something between 0 and 10 as our radius out there, right? Nothing super huge, nothing negative like that. So let's go ahead and see if we can do this. So I'm now going to use my formulas. I want polar coordinates. I want r and theta. So here's my equations for r and for theta. So the first thing I'm going to do here is compute r. This should be the square root of x squared plus y squared. And in this case, that's going to be for us the square root of 3 squared plus 7 squared. 3 squared is 9. 7 squared is 49. 9 plus 49 is going to be 58. And I'm not going to get a decimal out for this right now, but I do just want to estimate it real quick. The square root of 49 is 7. The square root of 64 is 8. So this should be like 7 point something. I'm picturing like a 7.5 or something like this for the length of this line that we're going to be experiencing right here. So I'll say it's about 7.5. I don't know. I'm just estimating that in my head. I know it's between 7 and 8. When we go to compute our angle associated with this guy, we're going to do our tangent inverse of y over x. And we're going to have no way to avoid using our calculator on this one. This is pretty mandatorily calculator area right here. I'm never really going to know these tangent inverse values that I'm looking for right here. But I can set up my statement, theta equals tan inverse of our y value is 7, our x value is 3. And if I go to my calculator and do this, and by the way, I'm going to do this in degree mode just because I'm trying to help myself out with my estimate here. I'm anticipating something in the ballpark of like 70-ish degrees. And I'd feel pretty good, honestly, if I got anything between 45 and 90 really out there. So I'm going to go to my calculator. I'm going to make sure I'm in degree mode. And I'm going to do my tangent inverse of 7 divided by 3. And when I do this, yeah, I feel like our guess was really good right there. I'm getting 66.8 degrees right there. So that was a really good guess at 70 degrees for that one. So it looks like what we've done now is we've determined that our r theta point is going to be root 58, 66.8 degrees. And here, I don't know, I'm going to typically just round those to 1 decimal place right there. I don't think we got to get too specific. Degrees already break down to 360 of them in a circle, so 1 degree is pretty small. 1/10 of 1 degree then is very small, so I think that's good enough for accuracy for us there. So let's now do our second example, but we're going to see that there's one slight little thing that's a little bit different in our second example here. So in our next example, we're going to look at the point -2, -3. So let me just get rid of just this bottom half here. We're looking at the point -2, -3. And we're going to need to put that in its new spot here. So -2, -3. I know that lives -2, -3. I'm expecting something that's in the third quadrant over there. Again, it might be hard to estimate your radius, but you should definitely be estimating your angle. This is the thing that really matters right here. I'm picturing that I'm getting something that's a little bit closer to 270 than to 180 right here. So I don't know, like 240, 230, something like that. I'm seeing something in the mid to low 200s out here for my angle. Again, 270 is straight down. And we didn't quite make it a 270. So even like a 250, I wouldn't be surprised by that right there. So that's the angle I'm anticipating getting here. So let's go ahead and do these two parts. For our radius here, remember that what we're squaring is all of our x value. So this negative that's on here, the negative is sort of getting squared away. The square of -2 is 4, the square of +2 is 4. These negatives are completely insignificant in our radius computation right here. In fact, it's pretty typical that I'll just write this as 2 squared, even though it's officially -2 squared, because I know that squaring is always going to make us positive. But I'll write it appropriately here. But this is definitely a case where I just discard the negatives because I know that the squaring handles it for me. Here I'm going to see 4 plus 9, that's going to give me 13. So my radius here is the square root of 13. The much more interesting part, and the reason we're doing this whole dang example is for this part right now. When I go to compute my theta here, I'm going to get tan inverse of my y value is -3, my x value is -2. I'm going to go to my calculator and I'm going to throw in exactly what I've got for my tangent inverse statement here. Tangent inverse of -3 divided by -2. And it's going to tell me 56.3. And now I'm going to look at you and say, really? Where is 56.3? Well, where I see 56.3 degrees is actually that line up there. That's not where our point is. So what just happened right here? This is a little bit weird. What we really need to remember is that the tangent inverse function only will output things for us from negative pi halves to positive pi halves. If the angle that we're expecting to get is in the second or third quadrants, then tangent inverse is never going to directly give us that angle right here. Notice what kind of happened algebraically here. When we do things like -3 divided by -2 on the inside, officially those negatives should cancel. And that should leave us with +3 over +2 inside the tangent inverse. So what that really means to me is that tangent inverse can't tell the difference between these 2 points. Because if this point is at 2, 3, and this is at -2, -3, both of them will have the ratio of 3 over 2 inside of the tangent inverse if we're going to compute the angle. But only one of them is the one that we're interested in here. So finally, I'll ask you, what seems to be the relationship between these 2 points? Well, it seems to be that this point, the one that we actually want, is just 180 degrees additionally rotated from the one that we're actually getting out of our calculator here. So the important thing here is this. In a sense, our calculator lied to us. Well, it didn't really. Tangent inverse only outputs things from negative pi halves to pi halves, and it did. What we need to do is we need to understand that sometimes we need to manually alter our angle right here to give us the one that's actually the version of it that we were interested in. That's why drawing this picture matters so much to me right here. So this is really our goal right here, is actually that guy in the lower left. So what I'm going to do here is I'm going to go ahead and add on 180 to get me to the appropriate angle that's still got the same tangent inverse value here. And so I'm going to go ahead and just add 180 in my calculator, and I'm landing at 236.3. This definitely corresponds with what I was anticipating there. If 270 is straight down, then we didn't quite go to 270. 236.3 definitely seems to correspond with what I was guessing to anticipate right there. So you should see that when we do these conversions from rectangular to polar, polar to rectangular, there's really only one major thing that you've actually got to watch out for. The rest of it's just direct computation. The one thing you've got to watch out for is that the tangent inverse function will only ever show you these angles in quadrant 1 and quadrant 4. If your point is in quadrant 2 or quadrant 3, then you will need to manually adjust the output that you're going to get from your calculator when you compute the tangent inverse out here. And by the way, one last thing that you should do to verify this for yourself is you should go to your calculator and realize that the tangent of 56.3 is the exact same thing as the tangent of 26 or 236.3. If you take the tangent of each of these two numbers right here, you'll get the exact same value, and so therefore you should be convinced that they both do sort of correspond to that tangent inverse output that we're seeing right there, right? So watch out for your thetas. Computing theta is the only one where you've actually got to do a little bit of thinking rather than just direct doing right here. So we've come up with our r comma theta pair of root 13 236.3 right there. So it looks like we've converted some rectangular points into polar points here now. So next up, we want to talk about polar equations. And polar equations, what we want to think about is that for your entire life, every equation that you've ever written has been in terms of x or y, or at least maybe in terms of our trig class, we sometimes use that t variable, right, like sine of t or theta. But the point is, you always have one input variable, one output variable, and we typically think of these things as being in xy space. What we now want to think about is, can we instead write equations that are in polar form instead? We are again just going to keep on using our same polar equations over here, our conversion equations between these three. So let's go ahead and take a look at some equations here in example 4 and see if we can use these equations, see if we can rewrite these equations in terms of their other coordinate system. So I'm looking at example 4 now. In example 4, I'm giving you two equations that are in rectangular form. They're x's and y's. I want them in polar form. So let's go ahead and convert to polar. And I've got two equations that I want to do this with. The first equation is x equals 4. The second equation is 4xy equals 9. We're going to do a little bit of extra math with this one, by the way, something that's slightly beyond the scope of this class in a sense right here. Wait, is that even this? No, we're not. Sorry, that's coming up in a different example right here. We're good. Let's go ahead and convert these things into polar out of rectangular. So again, I say that these equations are in rectangular form because x and y are the defining variables. To convert into polar form means that I want r and theta to instead be the defining variables. So all that says to me is I don't want x's, I want r's and thetas. How can we get rid of x in terms of r and theta? Well, I've got that right here. It looks like all I have to do is rewrite this as r cos theta equals 4. And I want you to notice something that's kind of interesting that's happening here for us. X equals 4 is a really simple equation. What graph does it actually describe? You should be able to answer this, by the way. The graph of x equals 4 is just the graph of all points that have an x value of 4. So when I'm thinking about the graph of this line right here, all points with an x value of 4, it should just be a vertical line right there. And that's the graph of x equals 4. And here's what I kind of want you to notice. This equation, even if you're less comfortable with like trig and polar coordinates, even if you're equally comfortable with trig and with polar coordinates as you are with non-trig and rectangular coordinates, this equation is more difficult to work with than this one right here. Here we have two variables that need to be described to make the graph. Here we just have one variable that needs to be described to make the graph. And the reason why this is the case is because a straight line is very well described with rectangular terms. A straight line is pretty awkward to describe as far as what angle do we need to go to and what distance do we need to travel to get to each point on the line. This is rectilinear is what I would say. It's based on straight line parts. Therefore, it makes sense to me that rectangular coordinates is the most concise way to state this relationship. We're going to see relationships exactly like this in a second when we do example 5 and we go the other direction. We're going to see shapes that are more circular are typically easier to write in polar, and shapes that are circular are typically harder to write in rectangular because circles and rectangles are quite a bit different here. Finally, I do want to say that this graph right here also, or this equation, is pretty typically written solved for r, although that's not always the case that we do this. But for some coming up examples that you'll look at here, looking at this as 4 over cosine theta is sort of a general structure that the book suggests is something that you should be able to recognize there. Our second one over here is going to be pretty similar. I'm just going to do some extra simplifying steps along the way. So in 4xy equals 9, we want to convert into polar. That means I don't want x's and y's, I do want r's and thetas. Again, I do know my two equations here for x and y, so I'm just going to go ahead and sub those in. So I'm looking at 4 times r cos theta times r sine theta equals 9. And what I'd like to do is just write this as simply as possible. Technically speaking, I guess, I'm done in the sense that it's in polar form, but this doesn't seem to be the most convenient way to maybe handle this. First thing I'm seeing is it looks like we have r times r here, so I think I can kind of rewrite this a little bit as 4r squared cos theta sine theta equals 9. The next thing that I'm seeing here is when do you recognize that we have sine theta times cos theta, and when is that an easier thing for us to rewrite as a simpler term right there? What I'm thinking is 2 times cos theta sine theta is the same as sine 2 theta. I'm remembering my identity here that says sine of 2 theta equals 2 sine theta cos theta. All right, there's the identity that I'm recalling from our identity section out here. And I do have that. In fact, there's 2 times 2 cos theta sine theta. So here's what I'm going to do. I'm going to use one of the factors of 2 from 4. There'll still be another factor of 2 left over. And I'm going to use the cosine theta and the sine theta to rewrite this as a sine of 2 theta. So I'm really going to be left with 2r squared sine of 2 theta equals 9. I think this is about as tightly as I could rewrite this statement now. Again, I used one of the 2's from 4 to join up with the cosine and the sine to make 2 sine theta cosine theta, which I rewrote as sine of 2 theta. So I've at least reduced this now down to one trig function. And what I would anticipate being able to ask you is things like, I am interested in all points that are on this graph that are 3 units away from the origin. Well, if they were 3 units away from the origin, then I can find what angle we need to traverse to get to that specific point. If r was 3, then r squared is 9. We could divide that over and get 1. Divide both sides by 2 and get a 1/2. We would then just have to solve the equation sine of 2 theta equals 1/2. That literally might have even been one of your test questions right there, right? So we can certainly do that. So we've converted this rectangular equation into not just into polar, but into a nicer simplified version of polar form using a little bit of our identities right there. And so again, we're just really using our conversion equations over here to rewrite things in one format and another format. We'll see that this is slightly more exciting. Now let's go ahead and look at example 5 right now, and let's flip this, let's convert into rectangular, and we'll see there's a little bit more excitement there. I kind of do like those ones a little bit better. There's a little bit more going on. It's not clear to me what my best format is, I guess, in my polar form, for example. It's not clear to me that either one of these is preferable to the other as far as helping me do like any amount of graphing. So really here, like, I don't know, I technically can solve this equation for r, but it's not clear to me that that's something like I should do. So that's why I'm just ending right here. When we convert into rectangular form, we're going to see that we're back in xy land, but we're going to see a lot of equations that don't necessarily want to be solved for y either. So again, we'll kind of have to make some judgment calls on like when do we stop in lots of these cases here. But I think what we're going to see is a bunch of pretty typical, or what we'll see is a bunch of pretty consistent formats that we end up getting out. So in example 5 here, we want to go ahead and convert polar equations into rectangular. The polar equations that I'm giving you here, let's just do these one by one. First things first, the equation r equals 4. Well, r equals 4 is a very simple equation here. And you should know what this graph is, by the way. This should be the graph of all points that have a radius of 4 from the origin. What shape is that going to make? Well, it's all points that are 4 units away from the origin, exactly, with any angle. The angle hasn't been specified. So it seems like this should be a circle. If I'm going to convert this into rectangular, I know that r is the same thing as square root of x squared plus y squared. And pretty typically we write this without the square root. I'm just going to square both sides here and write this as x squared plus y squared equals 16. And it turns out that what this equation is, as we can see, since these must be equivalent to each other, is that x squared plus y squared equals 16 is the equation of a circle with a radius of 4. And again, I think it's worth stopping and recognizing which of these two representations of the circle is easier. I think this one's a lot more complicated. This one takes 2 variables. The variables are squared and added together. There's a whole bunch of stuff going on right there that makes that a little bit tougher to see. On the other hand, r equals 4, you're not going to get simpler equations than that in life. And the whole point to me here is that since the graph is a circle, it's definitely going to be better described in polar coordinates, because polar coordinates are helping us describe circular type positioning. There's no straight lines in here, no rectangles, so rectangular coordinates are a little bit less convenient for us to describe that shape. So the point that I'm kind of trying to get across here is that the reason that we even have 2 different coordinate systems is because things that involve straight lines are better in rectangular. Things that involve circles are better in polar. And we might want to forcibly convert into one of those scenarios based on the type of objects that we're dealing with, because it might kind of simplify our scenario here. R equals 4 is definitely simpler of a statement than x squared plus y squared equals 16. In our next example here, we are looking at r equals 4 sine theta. And this is where this gets to be, I really like these. This is a little bit more of an algebraic adventure here. So my goal is to rewrite this in terms of x and y. Well, I do know that I could replace r with the square root of x squared plus y squared. I could definitely do that right now and probably like square both sides to get it out. Right? But my question is, what am I going to do over there? Because 4 sine theta, I don't have anything that's like a 4 sine theta over here. And in fact, just ignoring the 4, I don't have anything that's just straight up sine theta. I have r times sine theta right there. And I don't have an r in front of this sine theta to go along with it. So here's what I'm thinking I'm going to want to do. R could be rewritten as it stands, square root of x squared plus y squared. Sine of theta can't quite be rewritten as it stands because I need r sine theta to get a y. not just a standalone sine theta. So since sine theta really wants a buddy of r hanging out up front, what I'm going to do here to help myself out is I'm going to go ahead and I'm not going to square both sides. I'm going to multiply both sides by r. And that's going to leave me with r squared equals 4r sine theta. This is good for me because r squared is a really simple quantity for me. In fact, when we square r, we just get x squared plus y squared, right? If r is the square root of x squared plus y squared, then when you square it, you just get x squared plus y squared. And on the right, I've done myself a favor because now I do have an r sine theta. R sine theta is exactly just y. So it looks like this is equal to 4y. So I'm going to do some more algebra right now. I don't expect you to do more algebra. If CR were to change their curriculum orderings to require college algebra to be before trigonometry, then I would definitely expect you to do more with this. Since I know more than half of you haven't taken college algebra yet, and you're going to take that next, here is a topic that you're going to visit in college algebra. So again, I'm going to do this right now to relate this problem back to this problem right here, but I wouldn't necessarily expect you to be able to do this. If I'm saying to you, convert this into rectangular, I'm cool with you stopping right here. The book is definitely going to continue on because the book thinks that you already know algebra because that all happened in the first 8 chapters and we're in chapter 9. So just so that you know kind of where our expectation level is at right now, I'm good with you just getting to here, but I am going to show you what the book does and what any other math person would do to kind of wrap this guy up. So if I'm looking at the equation x squared plus y squared equals 4y, this feels a lot to me like my equation of a circle that I had over here, where it looks like this circle had a radius of 4 because the square root of 16 is 4. But I don't feel like I get that same action here because that's not a constant. That's a y grouping. So what I really want to do is I really want all my y's to hang out just in one place and to be squared like we had here. So here's the algebra steps I'm going to do. First, I'm going to move this 4y to the other side to hang out with its y squared buddy. And what I really want is I really want a single y term squared. So what I really need to do is what we refer to as completing the square on y squared minus 4y. So I'm going to kind of like put some parentheses around here just so that we're thinking of those as one group that we're sort of working on. I'm all good with the x squared. That has no issues there. This I want a square instead like out there. I need to figure out how to do this algebraically. So here's what I'm going to do. X squared plus, what I'm going to do is I'm going to bring in a special additional term here. What I know is if I want this to be a perfect square that is exactly a square of a binomial, then I can divide -4 by 2 to get -2, and I can square -2 to get +4, and that informs me that +4 is the special C term for this quadratic that's going to make this a perfect square. But since I've added 4 onto the left side of our equal sign, I also need to add 4 onto the right side of our equal sign. And what this is allowing me to do, and with a little bit of algebra here with our quadratics, we'll be able to see that this is going to give us x squared plus y minus 2 squared equals 4. And so ultimately what we're going to end up seeing for this guy is that this is the graph still of a circle because we have x stuff squared plus y stuff squared equals a constant. X stuff squared plus y stuff squared equals a constant, still in our circle format. And it looks like we've made no adjustments to our x terms. But it looks like we need to plug in an additional 2 units of y for this to be 0. That's going to move our graph up 2. We need 2 additional y units to get back to the same place that we were. And just like the square root of 16 gave us our radius of 4, the square root of 4 should give us a radius of 2. So I think that what we're looking at here is a circle that has a radius of 2 that's been shifted up 2 units. So what I'm expecting for our graph right here is a circle that's sitting on the x-axis. It's got a radius of 2 units, so 2 from the center, but we've shifted it up by 2, so now it's just sitting right there on that axis right there. So again, if you can get to here, we're good with that. But if you have taken college algebra, then you should be able to get to here with a little bit of completing the square action and seeing our general form of a circle that's right there. Finally, let's go on and do our last example right here, r equals sine theta minus cosine theta. All right, and so again in this example, what I'm seeing to myself here is I do have some R stuff, but it looks like I've got some sine theta and cosine theta that don't have an R attached. So again, it looks to me like what I'm interested in doing here is getting an R to go with each of these terms so that I could rewrite them in terms of x and y here. So let's do kind of our same maneuver as last time. I'm going to multiply the whole equation by R. That's going to give me r squared equals r sine theta minus r cos theta. I'm going to go ahead and rewrite r squared as x squared plus y squared. This is going to give me r sine theta, that's just y, minus r cos theta, this is just x. So we're in actually the exact same boat as we were in the last one. This is going to be some format of a circle. I know it's going to be a circle because I have x squared plus y squared, but I think there's going to be some adjustments to the circle that are going to get made, some shifts based on the x and y that are also sitting over here. So as with the last problem, if you're doing this problem, I'm good with you getting to right here. I'm going to go ahead and do just a smidge more algebra to kind of wrap this up, but if I were to tell you to convert from polar to rectangular, I'll be pretty happy if you can get to writing this statement for me right here. So let me just wrap up doing some algebra here. I'm going to kind of do the same thing as I did before here, and I'm going to say this should be x squared plus x. I added x to the other side to hang out with x. I've got a y squared minus y equal to 0. What I want to do is say I currently have 1x. 1 divided by 2 is 1/2. 1/2 squared is 1/4. So that says to me what I want here is x squared plus x plus 1/4. That will condense down to x plus 1/2 squared. Similarly over here, negative 1 divided by 2 is negative 1/2. Negative 1/2 squared is positive 1/4. So I'll get a y squared minus y plus 1/4. And we need to realize that twice now I've added 1/4 to the left side. 2 copies of 1/4 is 1/2. So I need to make sure I also add that to the right hand side. So 1/4 and 1/4 were added. 1/4 and 1/4 were added to the right hand side as well. This y grouping is going to condense very similar to how the x grouping condensed, y minus 1/2. And on the right hand side, we still just have that 1/2. All right, so how do we interpret this? Well, it looks like we can get away with plugging in 1/2 fewer of our x values than we used to have to for this term to be 0. So that's going to slide us to the left by 1/2. We need to plug in 1/2 more of our x values than we used to for this to be 0. So that's going to slide us up by 1/2. And finally, we know that the square root of our constant term on the end is going to be our radius. So it looks like we're going to get the square root of 1/2 is going to be our radius here. So this is going to be a circle centered at negative 1/2, positive 1/2, with radius square root of 1/2. And by the way, notice that square root of 1/2 is really just 1 over root 2, which is actually root 2 over 2, which is a value that we're previously comfortable with here. So again, a little bit of extra algebra here. We've got this completing the square on some quadratic terms right there, but that does really get us into our general form of a circle to where we can interpret our information here. As far as our center and our radius goes of that circle. So a little bit more there, but what I'm particularly interested in is, can you take this polar equation here, recognizing a very common polar trick of multiply through by r to get our trig functions to have an r partner, so that we can rewrite things in terms of x's and y's overall right there. So there's our example 5. Coming up on example 6, I'm interested in us talking about some of our standard shapes that we end up seeing here. And so this is really coming back to our simplified things right here. Which things are simpler in polar, which things are simpler in rectangular? Here's the question I'm sort of asking in example 6. And how should we recognize those general formats? So in example 6, I'm really asking you to do 4 things, but they're really the 4 simple things right here that we want to identify. So I'm going to graph the line y equal x. So let's just do these part by part here. Part A, graph the line y equals x, and then convert it into polar and solve for theta. So this is like the simplest line that we could ever draw. You should be thinking things like y equals mx plus b. You should notice that our m is a slope of 1, our B is a y-intercept of 0. So what I'm thinking to myself, if I'm graphing this thing, is it's just this line of slope 1 with a y-intercept of 0 right there. What I want to do is I want to convert this thing into polar and see what the equation looks like and then relate that idea back to my graph. So I'm going to convert this into polar. I know that y is the same thing as r sine theta. I know that x is the same thing as r cos theta. So my first algebraic move here is to say, it looks like we have an r on both sides that we can divide away. So let's literally just cancel off these r's right here. I divided both sides by r. And I'm left with sine theta equals cosine theta. A couple different ways that we can go about this here. I think that if I'm trying to solve the equation sine theta equals cosine theta, the thing I'm thinking is if we divide both sides by one or the other, then we can get to a single trig function. I'm thinking, which one do I want, sine over cosine or cosine over sine? I like sine over cosine because that's tangent. So I'm going to do sine theta over cos theta equals 1. That should be tangent of theta equals 1. And we know at what angle we receive a tangent of 1. We should be picturing in our unit circle out here, we experience a tangent of 1 whenever our x and y values are exactly the same. And hey, that makes sense. Our x and y values are exactly the same as when we get to a tangent of 1. And if we were to perform the actual computation tan inverse of 1, our calculator is certainly going to give us the answer of 45 degrees. So notice that what we just did right here is we converted from rectangular into polar, and we solved for theta. And what theta did we find? It seems like the equations y equals x and theta equals 45 degrees are equal to each other. What I'm really looking for us to take away from this right here is the fact that theta equals 45, or in general, any equation that just is theta equals a constant, is always going to describe for us a line. It's the line of all points that make an angle of 45 degrees with the positive x-axis. Every single point, the infinite number of points on that line, they all make that 45 degree angle with the positive x-axis right there. So one interesting thing for us to notice here is that lines of any slope that go through the origin, they have to go through the origin. That's a really important part right here. Can always be described as just theta equals a constant. So for an additional example, if I were to say to you, graph for me the line theta equals 20 degrees, well, that should just be the line of all points that have an angle of 20 degrees. Right there. There's my entire line of 20 degrees. Notice over here we have negative radii. Over here we have positive radii. But all the points on that line make a 20 degree angle with the positive x-axis. So that's an important one for us right there. Theta equals a constant. That's just a line for us right there. So there's part A. Let's go ahead and take a look at part B. I think part A was actually our most work that we're going to have to do for one of these here, so that's good. So for part B, we are now looking at r equals 2. And I'm saying graph it, then convert to rectangular here. So what we have already talked about is that r of 2, this says, I want to graph all points that have a radius of 2 from the origin. Well, if I graph all points that have a radius of 2 from the origin, I'm just going to get a circle of radius 2. So I know that r equals a constant should be giving me circles. Theta equals a constant should be giving me lines. And the circles should be centered at the origins. The lines should go through the origins. When we have r equals a constant, theta equals a constant. If we convert this guy into rectangular, all we're going to see is square root of x squared plus y squared equals 2. And we square both sides. And I'm going to write this as x squared plus y squared equals, and I'm going to write this as 2 squared so that we see that this is a radius 2 circle. Remember that when we have x squared plus y squared equals a constant, it's actually the square root of this constant that's our radius, not the constant itself. Before we had one that was equal to 16, it had a radius of 4. It's the square root of the constant on the right. So a lot of times circle equations will actually be written like this so that you can easily see that that term is the radius that's right there. So that r equals 2 one, pretty easy, one that we've already seen. So it looks like if you want to give the equation of a circle in polar form, it's simple because circles are easy in polar. In rectangular, it's a little bit harder, but it does seem like we now know our general form of circles in rectangular format as well. Finally, for B and C, we're looking to graph a couple lines here, a couple more lines, or sorry, C and D. In part C, we're looking to graph y equals 2, I know that the graph of y equals 2, this says to me graph all points that have a height of 2. If we have a height of 2, then we are just this straight line right here. I'm noticing that straight lines are definitely things that should be easier to do in rectangular than polar. It seems weird to me to describe lines using circle information here. And we're going to see that when we convert it. If I convert y equal 2 to polar, then I'm going to be getting r sine theta equals 2. And that's certainly a slightly less nice form here. So I'm going to rewrite this as 2 over sine theta. And what it looks like to me is that in polar form, the equation of a horizontal line is always going to be, since it's a horizontal line, we're deciding what our height is. So heights are associated with sine. What is the height? The height is 2. So I can sort of see the line part of this here. Very much not obvious to me that that's a line, but since I know that this is a horizontal line of height 2, I can sort of see that. Horizontal line means that we're choosing the height. What height are we choosing? 2. Heights are associated with sine, not cosine. Right? Is our final example right here. Not much changing. All I'm doing is saying, let's let x be equal to 2. In this case, this is the set of all points that have an x value of 2. So it should be our vertical line here. We're going to instead have our cos theta equals 2, and we're going to get 2 over cos theta. So the good thing is that these two equations sort of match each other in a sense. For this one here, we are looking at a vertical line. If it's a vertical line, you are choosing your x-coordinate associated with everything in the line. X-coordinates are associated with 2. What is the x-coordinate of every point? Or sorry, x-coordinates are associated with cosine. What is the x-coordinate that we're choosing? 2. So even though this does not look to me like the equation of a line, it is. But I can sort of see that. I can see that we picked a width, cosine. What width did we pick? 2. And so I guess I can at least see those parts. So it looks like we can sort of fill out this table in a sense that I've suggested to you that we should maybe be aware of here. If we're talking about horizontal lines, if I am in rectangular versus polar, so a horizontal line in rectangular form, we have chosen a height of all of the points. All of the points have the same y value, so we generally give these as, and I'll call this y equals b, just as any old constant that's out there. So the height of our line is b. We've picked a line of height maybe 2, so b is 2. In this case, what we saw that our equivalent polar equations are always going to be equal to is r equals whatever that height was. And since we're picking heights, heights are associated with sine, so we're always going to get a sine theta there. Similarly, if we do a vertical line, not much else changed in there. We'll define these as x equals a, so I have a is my x stuff, b is my y stuff here. This is saying we've chosen a vertical line's location, which x value do all the points have on the line. So here we'll get r equals a over cos theta, because cosine is associated with our widths. We've got our skew lines with a slope of m equals, and what I call it here, b over a. Notice here, slope is usually your change in y over change in x. I'm associating b with my y points and a with my x points, so that all matches up right there. And if we have a line of slope b over a, then what I'm thinking is that my rectangular form here should really just be like y equals mx, or b over a x. What we ended up seeing though is that these should just be associated with a single angle, whatever angle we're traveling at. What we know is that we compute our angles as the y parts divided by the x parts. So I think I can list this equation over here as just theta equals a constant. What constant? The tangent inverse of b over a. It's the y parts divided by the x parts right there. Finally, we have a circle centered at the origin. A circle centered at the origin is always going to have an equation of x squared plus y squared equals r squared. The radius is always squared on that other side there. And much more simply, since circles are not rectangular, but circles are described by angles and radii, we get a very simple equation over here, which is just r equals, oh shoot, I don't have a variable for this now. I don't know, r equals c for a constant out there. The point being is that these two equations are constant equations. Theta equals a number, r equals a number. Circles and lines at a given angle are easy in polar. Horizontal lines, vertical lines are more rectangular type of ideas, and so they are very simple to state in rectangular form. Well, I guess the only like slight confusion here is like lines, we should be thinking rectangular, but since this is a skew line, it's really a line rather than having slope. You could think of this line as having just a constant angle, and that constant angle is exactly how we can define that line in terms of polar coordinates there. Finally, in example 7, what you should be doing is you should do example 7 in Desmos here, because I think that this is one of those, it gets a little bit hairier here. And what you should see is in our section 9.2, you're going to see some pretty crazy graphs that are out there associated with some of our polar stuff. You really should look through those and play around in Desmos for a while with some of those. I am going to ask you some questions sort of about some of those graphs, but they're certainly a lot harder. They're a lot harder to do by hand. These are things that I struggle to do when we teach in person, let alone from a distance here. So you really should spend some time in Desmos with this section. You should know that Desmos is cool with you using R and theta. To get theta, literally just type out the word theta, T-H-E-T-A, and it will replace it with theta. It does understand polar equations. So you should do things like graphing exactly this, add a slider bar for B, and watch as it just moves a horizontal line up and down on your screen. Another thing that you should notice is that in Desmos, it typically is always set up in rectangular coordinates so that there's always a rectangular grid. But if you click on the settings option in the upper right hand corner, you can change the grid to where it's a polar grid, where it's got circles and radial lines that are pointing out there. That might be your little bit easier way to go about graphing those things to get a visual sense. So you should really be spending a good chunk of time playing around in Desmos associated with this section here. Our conversion equations are pretty dang easy to come up with on our own and then to use as far as converting points in space, as well as converting equations and stuff like that. But getting some intuition for what our graphs look like really does matter. So make sure you spend some time in Desmos playing around with some of the more complicated graphs that you do see here. And I'll ask you some reasonable questions about those types of graphs when the moment comes up here. So if you have any other questions, go ahead and let me know. I don't think I made any mistakes on the board here. I did in one of my previous videos, and I at least identified it while I was making the video. I think this is good. If you see any typos in here, you should let me know so that I can kind of just like post a correction to this video here. But otherwise, let me know if you have any questions.